in question number 5, the particle has linear motion. So we can, for example, assume that the particle is traveling along the x-axis. So that's the x-axis. This is the positive end of the x-axis. This is the negative end, and maybe the origin is over here. Now in option A, it has been mentioned that the velocity and the acceleration have opposite signs, and we have to, and the conclusion which they have drawn in option A is that if this is the case, then the particle is definitely slowing down. And we have to comment upon whether this statement is true or false. To do that, let us take an example. Let us consider that the particle is situated over here. Let us further imagine that the velocity of the particle is greater than 0. Then, for example, you can imagine that the particle's velocity is plus 5 meters per second. Just as an example. Now this means that the particle is moving towards the right, because we have taken rightward as positive, and the rate at which the particle is moving, that is the velocity, is 5 meters per second. Now the acceleration is oppositely signed, so A is a negative number. A is negative. Let's not even take any example that A be any negative value. Clearly, if A is negative, it also means that dV by dt is negative. After all, dV by dt is A, and in dV by dt we know that dt, being a time interval, is always positive, and so if dV by dt is negative, that leaves us only one option, namely dV itself has to be negative, and dV stands for the change, the small change in V. The conclusion is that V changes by a small negative value, but the original value of V is given to be 5 meters per second. That's, we have taken it as an example, and so if V, which was first 5 meters per second, changes by a small negative amount dV, then this 5 meters per second is going to become a velocity which is still positive, but it's a bit smaller than 5 meters per second. And this change, of course, it happens in a time dt. So in this time dt, we can see that the speed of the particle was first 5 meters per second, and now it's going to be a bit smaller than 5 meters per second. So naturally that means that the particle is slowing down. Please note that in this entire solution, we have never used the fact that the particle is to the right of the origin. For example, the particle could be in some other place, maybe it's to the left of the origin, still moving at plus 5 meters per second, and the whole solution is valid for that case too. In other words, the particle will be slowing down irrespective of whether it is to the right or to the left of the origin, or indeed even if it is at the origin. Now let's see what happens if the particle has an original velocity which is negative. So the diagram has to be modified. The particle is going leftwards at 5 meters per second. Now this means that according to our sign convention, which is rightward positive, the particle would not have a positive velocity but a negative velocity, and so accordingly I'll just write minus 5 meters per second is the velocity. Now the acceleration has the opposite sign as compared to the velocity, so the acceleration is now positive. dV by dt is positive, and by the logic which we discussed earlier, it means that dv is a small positive number. So what this means is the following. In the time interval dt, the velocity was initially minus 5 meters per second, and after this time interval the velocity changed by dv, which is a small positive number, which of course means that the velocity is still negative. The change is small, so the velocity is still going to be negative, but it's going to be a bit larger than minus 5 meters per second. A moment's thought will convince you that in the time interval dt, the speed of the particle has decreased, and that's because the speed is the modulus of the velocity. If you are unconvinced, you can just take a simple example. Supposing that there is a physical quantity which is initially minus 10 units, and let us say that this physical quantity after some time it becomes minus 9.9 units. Now you can easily see that the quantity has changed by plus 0.1, and it changed from minus 10 to minus 9.9. Now you can have a look at what has happened to the magnitude of the quantity. The magnitude was 10, modulus of minus 10 is 10, and it became 9.9. You can easily see that the magnitude has actually decreased by 0.1, and that is the basis of the statement made previously that the speed has actually decreased. It's easy to show that this particular result is true irrespective of the position of the particle on the x-axis. So the position could be here, the particle could be going left at 5 meters per second, or actually at the origin going left 5 meters per second. It doesn't matter, as long as the velocity and the acceleration have opposite signs. We have now proved that the particle is slowing down, and hence option A is correct. Now we consider option B. In this option, the statement is that if the position and velocity of the particle have opposite signs, it necessarily means that the particle is traveling towards the origin. So let's take an example. Let us assume that the position, here it means the x coordinate of course, let's assume that the x coordinate is positive and that the velocity, which must have the opposite sign, is negative. And so in the diagram I'm going to show the particle over here to the right of the origin, since its x coordinate is positive. Now the velocity is negative. That would mean that the particle is traveling towards the left, because the leftward direction is the negative direction. And we can see quite clearly that indeed the particle is traveling towards the origin. Now we can look at the opposite case. In other words, let's assume that the x coordinate is negative and the velocity is positive. Now if the x coordinate is negative, it means the particle must be to the left of the origin, like that, and the velocity being positive, the velocity is towards the right, so the particle is moving towards the right. And once again we see that the particle is traveling towards the origin. So this would mean that statement B, option B, is correct. If the position and velocity have opposite signs, then the particle is necessarily traveling towards the origin. Now let us go to option C. Option C says the following: if the velocity is 0 at an instant, then the acceleration should also be 0 at that instant. To understand this particular statement and to grasp whether it is true or false, we must recall what is the definition of acceleration. The acceleration is the rate of change of the velocity with respect to time. The acceleration doesn't have anything directly to do with the value of the velocity. It only depends upon how fast the velocity is changing, or the rate at which the velocity is changing. Now this indicates that even when the velocity is 0, the particle's acceleration could be non-zero. As an example, you could consider that the acceleration of a particle is constant, let us say, and so the velocity is constantly changing from one value to the next to the next. Now during this process of change of velocity, when the acceleration is constant, it may so happen that the velocity passes through a zero value. I mean, the velocity could be positive, and then it decreases, it becomes 0, and then it decreases further to some negative value. During this entire time interval, there happens to be some acceleration, and during that time interval, it is also equally true that the velocity did become 0 for one time instant. So this is an example of how a particle can have non-zero acceleration in spite of having zero velocity for a particular instant. A practical example of this would be that of a stone which is thrown vertically upwards. Now we know that it travels up and then down, so this is an example of linear motion. So let us assume that it travels along the y-axis, which is, say, positive upwards. We know that the velocity of the stone is initially positive, and as it travels in the upward direction, the velocity decreases continuously until at the topmost point, when the particle is momentarily at rest, the particle's velocity is actually equal to 0. Thereafter, the particle travels in the downward direction, so its velocity is going to be negative along the same vertical line. Now all of this time when the particle was traveling, it was under the gravitational influence of the earth, and it was subject to the gravitational acceleration of the earth. In other words, during its entire journey, the acceleration of this particular stone was minus 9.8 meters per second square. In other words, it was 9.8 meters per second square in the downward direction. Now this acceleration is valid even when the particle was at its topmost point, because the Earth's gravity is still acting on the particle at that instant. So here we have a situation where the particle's velocity is 0, but its acceleration, which is minus 9.8 meters per second square, is not equal to 0, and this means that statement C is incorrect. Now let's see option D. It says if the velocity is 0 for a time interval, then the acceleration is 0 at any instant within that time interval. So for example, a particle which is moving along a straight line, we see that its velocity is equal to 0 in a time interval defined by some time t1 is less than or equal to time t is less than or equal to t2. In other words, the velocity is equal to 0 from time t1 to time t2. Now since the question uses the words within the time interval, let's suppose it to mean the time interval defined by t1 less than t less than t2. So when t lies in between t1 and t2, the statement claims that the acceleration must be equal to 0, and this is something which we have to ask ourselves, is it true or false? Please note that the interval which is now under investigation, this particular interval, the equality signs have been removed because of the use of the word within. In other words, we have to investigate whether the acceleration is equal to 0 or not for a time interval which begins slightly after t1 and it ends slightly before t2. To solve this question, we must be clear in our mind as to when is the acceleration of a particle said to be 0 at some time t. We remind ourselves that the acceleration is defined by dv by dt, and for this to be equal to 0, it is necessary that dv must be equal to 0. In other words, the velocity must not change in any small time interval dt which contains the time t. So in short, if we want to find whether the acceleration is 0 at some time t, we have to consider a time interval which starts from slightly before t and ends slightly after t. Then ask yourself the question, does v change in this defined time interval? And if the answer to this question is no, in other words, if v is a constant in the time interval which begins slightly before t and ends slightly after t, then our conclusion is that the acceleration is equal to 0 at time equal to t. Now we must check whether this particular condition, that is the acceleration is equal to 0, is valid for all times within our time interval. And if the answer is yes, then of course the acceleration is 0 at all times in that time interval. So let's again recall that our time interval, it starts slightly after t1 and it ends slightly before t2, and that's because of the absence of the equality signs. We also recall that the particle's velocity is always equal to 0 in the entire time interval which begins at t1 and ends at t2, including time t1 and including time t2. And because of this condition, it's quite easy to understand that for any small t which satisfies this particular condition, for any such small t, the velocity is equal to 0 for any small time interval containing that t. And since the velocity doesn't change in that small time interval, we can say that the acceleration is equal to 0 at the time t. Even when our time interval begins, which happens slightly after t1, even then the acceleration is equal to 0, because the velocity was equal to 0 even when t equal to t1. Remember, there is an equality sign included over here. In other words, the velocity was equal to 0 even before our time interval began, and hence there is a small time interval which contains the beginning of our time interval. Our time interval begins slightly after t1. So there is a small time interval containing the beginning of our time interval, during which the velocity is equal to 0 and hence constant. And that means that the acceleration is 0 even at the beginning of our time interval. The other confusing case is what happens at the end of our time interval. Remember, our time interval ends slightly before t2. So once again, the equality sign over here tells us that the velocity is equal to 0 even after or slightly after our time interval ends. So by the same logic, we can prove that the acceleration is equal to 0 even at the end of our time interval. Now the time instants in between this and this, those are pretty easy to understand. In fact, we have already proved earlier that at all of those time instants, the acceleration is equal to 0. And hence, we have concluded that the acceleration is equal to 0 throughout the given time interval, which makes option D a correct option.